Welcome to Data Science 1, Probability, Covariance. Things we're going to need to remember. We're going to need to know what a joint probability distribution is. We're going to have to remember the expectation rules and the variance rules, but you'll see how this all works out. Now, we're not really going to go through a big example here because I just have to explain the idea of covariance first. So later we'll look at an example where we put everything together. So just hang on for that if you're trying to figure out where is all this going, because this lately has been kind of theoretical in the sense that we don't have numbers to put in this thing. It seems like just a bunch of math, which is what probability devolves into. Probability is a branch of mathematics. All right, so here's some rules of expectations that we've had. I'm not going to go over them all again, but they're here from two other videos. You can go back and look at them and see where they came from and see why they work. The last one is the one we're really interested in. It says if x and y are independent, then the variance of x plus y is equal to the variance of x plus the variance of y. And I didn't show you why that's true yet, and I still won't show you that yet. There's just so much math to go through in order to get there. All right, so let's look at variance again. So let x and y be random variables with the expected value of x being mu x and the expected value of y being mu y. The variance of x being sigma squared sub x, the variance of y being sigma squared sub y, and the joint probability distribution function is f sub xy xy. Ugh, that's a mouthful. All right, so this is the variance of x and y. So I'm just trying to swap out the notation because depending on where you look in different literature, sometimes you'll see it written this way and other times you'll see it written this way. So I'm just trying to expand things out. So this is what we're interested in right now. So we're going to say, well, what is this? Well, it's the variance, right? And that would be this squared. Okay, so we have here x plus y minus mu x plus mu y, which is the expected value of this bit. Okay, so if I rearrange things, I'm just going to move the mu over, it has a minus sign in front of it, and move the y into this. And remember, when I distribute through, the minus sign will go through with that. Okay, then when I expand this out by considering this as one term and this as one term, then what we end up with here is x minus mu x squared minus 2 mu x, y minus mu x, plus y minus mu y quantity squared here. Now, we're seeing pieces here that we've seen before. So let's look at that. So when I run the expectation operator through, I end up with a piece here that I've seen before, and I end up with a piece here that I've seen before. But this thing in the middle I haven't really dealt with before. So, well, this piece is the variance of x. This piece is the variance of y, and notice there's a plus sign on here. And then we have this minus 2, the expected value of x minus mu x, y minus mu y. And that makes you go, what is that thing? Okay, and this is the thing we're talking about. This is covariance. Okay, so this is the idea of covariance. It measures how x and y vary together. For example, if we expect x to be greater than its mean and y to be greater than its mean simultaneously, then we would expect the covariance to be positive because a positive times a positive is positive. Here, if we expect that when x is less than the mean and y will be greater than its mean, then we would expect this to be negative. And similarly, if we expected x to be greater than its mean and y to be less than its mean, then we would expect, if we multiplied them together, positive times negative would end up with a negative. And they vary in the opposite way. And notice it says tends to vary because they're not absolute, because this is variance. Things are random. We can't expect everything to behave exactly as we think it will. All right, and if they're both below the mean at the same time, then we would expect the covariance to be positive. And that means they tend to vary in the same way. So, can we reduce this formula down to something even better? And we're going to work on that now to get another formula. That way, when we end up doing a big example, we don't have to compute everything. Okay, we've already got lots of pieces to compute, but we want to boil it down to the minimum number of things that we have to compute in order to make this work. All right, so if I take this right here, expand it out. That's all I did is expand it out with the FOIL method. Okay, and then run the expected value through this because it's a linear operator. And then I realized that this is a constant and this is a constant, so we pull those constants out. And I noticed that this whole thing here is a constant, right? We know the value of that. It's an expected value. It's a number already. All right, so then we end up with this once we say, well, the expected value of y is mu of y, and the expected value of x or y is mu of y, and we end up here, and it boils down to that a whole bunch of things cancel out, and we're ready to go. So this will help us speed up computation here. But the big thing is we'll need to be able to calculate this. We'll need to be able to calculate the means, which we already know how to do. So we just have to worry about this, and we'll do that in another video. Because right now we're already running up here on almost 6 minutes, and I try to keep these videos short, give you the idea, and then we'll work through the gory math later. But right now, this is the basic idea. And then the next video we're going to look at is conditional expectation, and after that we'll worry about doing the big example. All right, so see you in the next video.